Okay, so welcome all of you to the live session, and we will discuss some questions again today. So let me share my screen. Alright, so I think the screen is visible now. The screen has gone, right?
Yes, not visible.
Okay, let me try once again. Can you see the screen?
Yes.
Okay, fine. So last time we left some questions, so I will continue from there only. So we were discussing something about cycloatomic extension, Kumar extensions, cyclic extensions, and we saw what is the relation among these three kind of extensions. And then we want to know, suppose we have, if we can recall the definition of cycloatomic extension, that is, first of all, you need to fix some condition on the base field, let's say. So I'm just recalling. So let me recall first. So just a recall, we have K over F. We said this cycloatomic extension, if we say K is the splitting field of some polynomial x power n minus 1 like this. So moreover, we have one more condition on F, that if you can recall, then characteristic of F is either 0 or characteristic of F should not divide n, which has to be of course prime. And F, well, I don't think we need a condition on whether it has a root of unity or not. Can you recall that? Does it have root of, does it require a root of unity type to contain or not?
F contains an nth root of unity.
Yeah, so if I'm saying that this condition is enough, do I have to add some more condition that F should have one root of unity at least, or do I, there is no need to add that condition?
F contains an nth root of unity.
Well, we want that K to be the splitting field of this polynomial, then anyway we know that F contains 1, so it contains at least one root of unity. I mean, I think for cycloatomic extension we don't require, right? However, for Kumar extension we require, right? So I think if you recall, then we just named that a field should be having characteristic 0 or P, where P should not divide.
Dimension of K over F is n.
Well, if we just say that this is the splitting field of, we don't have to say that it is actually degree n. In fact, it will not be degree n, as you can see that x minus 1 time that polynomial, this polynomial is always like that, and 1 is always there in f, right? So degree will be of course less than n. It cannot be exactly n, that you cannot say.
Contains primitive nth root of unity. No.
Well, I think if it contains, then it will contain all, right? So because all of them are the powers of the primitive. So
okay, only these two conditions.
Yeah, for cycloatomic only these two conditions. And then we saw that in order to know that what is the degree of this extension, it is enough to know the irreducible polynomial which has primitive element of this polynomial as a root of that. So that means what I'm trying to say, suppose we are looking for q, f to be q, and I'm trying to look at, let's say, zeta 8 over q. Of course, directly I don't know what is the degree of this extension, but if we can see that what is the irreducible polynomial where zeta 8 is a root, then I can say the degree of that polynomial will exactly be the degree of the extension. Now, there are several ways. You, first of all, either you look what are the how the primitive root look like, and from there you try to build a irreducible polynomial. But there is one more criteria, that is cyclotomic polynomials. So if you recall, cyclotomic polynomials are quite useful, and they will give me the degree of the extension of cyclotomic extension. So okay, so if you recall, then let's go to the question 1. So it says that x power n minus 1 is the product of these cyclotomic polynomials. So can you recall what is the cyclotomic polynomial phi dx? Yeah.
Is product
Product, yes, product of
x minus that psi carries over primitive dth roots of unity.
exactly. It should be primitive dth roots of unity. However, if you say x power n minus 1, that has to be product of zeta all nth roots of unity. Okay. Then only if you take all n roots, then only you will get a degree n polynomial. All right. So this is that we know. This is one. This is one equality that we know about the polynomials. Now, suppose knowing that, can we tell what is phi 1x, phi 2x, 3x, phi 4, phi 5? Yes.
Phi 1x that is 1th root of unity, just only 1 x minus 1.
Yeah, one is itself is the 1th root of unity and moreover primitive. Yes. What about phi 2x?
Minus 1 is the only primitive 2nd root
Exactly.
of unity.
Yes. So since minus 1 is only primitive 2nd root of unity, so therefore I should say that it should be minus of minus 1, which is x plus 1. What is phi 3x?
Omega and omega squared are primitive
Yeah,
3rd
omega.
roots.
Correct.
So x minus omega into x minus omega squared.
Yes, so x minus omega square. And if you expand it, it will be minus of omega plus omega square x plus omega cube. And we know that omega is a primitive root of unity, 3rd root, so it should satisfy this omega cube equal to 1. And we also know 1 plus omega square is 0. So therefore this is plus x plus 1. Alright, so this is a phi 3x, then we are phi 4 and phi 5. Quickly we will see.
X squared.
Square plus 1, why? Because in minus ir.
Pi 3 of x squared plus x plus 1.
Sorry, I don't get what are you saying?
Third one, pi 3 of x.
Yeah.
X squared.
Okay. So x square plus x plus 1. Exactly. Phi 4, why? Because in minus I are only primitive 4th root of unity. So if I take x minus I, x plus I, this is how this polynomial will be. What about phi 5x? Well, remember P is prime.
Pi is prime.
Yeah.
So psi to psi power 4.
Sorry.
The primitive 5th roots.
Yeah, primitive roots. But I'm giving you a hint that P is a prime here, which is 5.
Yes. That cos 2 pi by 5 plus I sin 2 pi by 5.
Okay.
Then square of that, cube of that, power 4.
So among this we have 0, 1, 2, 3, 4, all are primitive, right? Why? Because 5 is prime. Agree?
A equal to 0.
Yeah, but I don't think this, I mean, this is a good way to look at the roots and then find out what are the primitive roots if you know this is prime. Because you know that 5px is, you have to know the primitive roots, but you also know x power p minus 1 is nothing but x minus 1 and x power p minus 1 plus 1. You know that this is irreducible, right? And any primitive pth root of unity satisfies this, right? So instead of this, you have to take this polynomial, and therefore uh, this should be the case, right? For prime, you don't have to do any computation. I think this is simple, right? Do you agree this?
Yes.
Okay, so and therefore, all right. So can we use this knowledge to find the irreducible polynomial for the eighth root of unity? So suppose what I'm trying to ask here is this. Suppose we are given q zeta 8 over q, and I want to know the dimension of, degree of this extension. So since we know that the degree is nothing but the polynomial, irreducible polynomial satisfied by zeta 8. Now, knowing this phi, phi 1, phi 2, phi 3, the knowledge of computing phi dx, that means cyclotomic polynomial, can that help us to find the degree of this extension? Yeah. Of course, for this we don't have to, we can, there is one way that you find what is zeta 8. Okay, find zeta 8. Find its polynomial, in fact, irreducible polynomial satisfied by zeta 8 over q. But I'm saying there is one more way, which is the way of using phi dx. Can you see that? Why? Because there is a result which says that your phi dx actually, in fact, your recall phi n x for any x, it's always an integer polynomial over x. Other thing, this is always irreducible. Irreducible polynomial of primitive nth root of unity. Do you agree? These are certain results that we know. And the degree of phi n x is same as the Euler phi function n, right? Now, I'm saying that this knowledge is enough to get the dimension or the degree instead of going to find what is the primitive root itself. This is okay, right?
Yes. So that is
So, yeah. So then what is the answer?
phi of n.
Well, what is n? For n is 8, right?
N is 8. Phi of 8.
Yeah. So either you compute phi of 8 or you compute the function cyclotomic polynomial phi 8x. So let's compute first of all phi 8x. So we know that in order to know this, it's not direct how do you find it, but you can use this formula that x power 8 minus 1 is product of phi dx where d divides 8, right? Let me first compute what is Euler phi function. So what is phi 8? Yeah.
That is the number of integers relative to prime. The 8, that is 4, I think. 1,
Okay.
3, 5, 7, 4.
This is one way. Other way is if you have some prime power, then Euler phi function says that you simply take right this, right?
Yes.
So it's 8 minus 4, that is 4. Same as what you told, this is same as cardinality of the set 1, 3, 5. Sorry. Phi 8 is same as the cardinality of 1, 3, 5, 7, which is again 4. So we anyway know that the degree of is 4. Let's compute through this formula that really the degree of this irreducible polynomial, is it 4? So can we compute that using this knowledge?
Phi 8 of x.
Yeah, this is phi 1x, phi 2x, phi 4x, phi 8x. Why? Because you are product over all divisors.
So we
And
know
what-
phi 1 to phi 4.
Yeah, you know, this knowledge you know already. So use that, phi 1, phi 2, phi 4. So it is x minus 1, x plus 1, x square plus 1. So let's write x minus 1, x plus 1, x square plus 1. And here you can write this as x4 minus 1, which is x square minus 1, x square plus 1, and then x power 4 plus 1. Right? Now this is x square minus 1, this is x square plus 1. So we can simply cancel it. What is 5tx? Sorry, 5 8x. So simply, if you see from here, it is just x power 4 plus 1. So naturally, you took zeta 8, but the degree of your extension is just 4. So of course, just looking at which primitive root you have, you cannot tell me the degree, but only for one case you can tell me if it is prime. So if I ask you what is the degree of this extension, that you can tell, right?
P minus 1.
Yeah, this is p minus 1. Exactly. All right, so this is the way we can use to find the degree of the dimension, sorry, extension. Now, question 2 is, suppose, I think this is anyway just the repetition. So if a prime, what is the order of Galois group of Q zeta P over Q? That we know, I guess. So let's repeat again. So Q zeta P over Q, we know that this degree is same as the degree of irreducible polynomial of zeta P, and that we know that has to be because we know that x power P minus 1 is some product of phi Px, where that phi dx, where d divides P, which is just phi 1x and phi px. Therefore, from here itself, you can say that phi px is nothing but, because here you can write x minus 1 times 1 plus x power p minus 1. Phi 1x, you know it is x minus 1, that get cancelled. So, therefore, it is just phi up to xp minus 1. So, degree of your phi p, the cyclotomic polynomial, is p minus 1, and therefore this is the degree of your extension. This is fine, right?
Yes.
And as we just saw that the statement does not hold, so question 2 says, is the statement hold, which, so we know that degree is p minus 1, and if I replace p by 8, then we saw that this result does not hold, because degree of, so we know, because degree of q zeta 8 over q, we saw it is 4, which is not equal to 8 minus 1, which is 7. So therefore, this result of which is hold for prime does not hold for composite numbers. All right, so now here is question 3. So now we will come back to some new stuff which has been discussed in the last videos. So what is the difference between simple extension and simple radical extension? Yeah.
Simple extension satisfying just one condition, namely f of I equal to f of I minus 1 of alpha.
But I am sorry, I'm not getting your fi minus 1. Are you talking about some tower?
So K is a simple extension of F
Okay.
if there exists an element alpha in K such that f of alpha equal to K.
Exactly right. So if this is the case, we say the extension is simple extension. But what if I say what is a simple radical extension? Yeah.
Radical extension means in addition to this, alpha power n must be an element of f for
Okay.
some integer, positive integer.
So first one, hold plus alpha should be, or I should write like this, alpha power n
Belongs to f
f
for some
n.
n.
Yeah, exactly. So if such a thing is there, then k equal to f alpha over f is a simple radical extension. Right. Okay, so can we see some example?
Q root 2 is a simple
Q root 2 is simple as well as simple radical, right?
simple radical extension of Q.
Yeah. So this is a simple
Q
radical.
omega over Q.
Q omega over Q, where omega is primitive root of third root, let's say. This is also simple radical. Why radical? Because omega cube is 1, right? Alright, so now suppose we go to question 2 now. Let K over F be a finite field extension and alpha belongs to K. When do we say alpha is solvable by radicals over F? I'm just repeating certain things because these are quite useful. Maybe we have done in this some of the things we did last also. Yeah, so
Alpha is solvable by radical over f.
yeah.
So there exists a tower of fields.
There exists a tower of fields, yeah.
F naught equal to f, f equal to f naught, contained in f1.
Okay.
And alpha belongs to K is there. And all these extensions are simple extensions.
All
F1
these are
is a
extensions.
simple extension of f naught. In addition to that,
Okay.
some alpha power n1 belongs to f1.
F1.
F naught.
Well, if you want to say this is just soluble by radical, if we say there exists a radical extension in which our alpha lies, that is enough, right? This is what you are trying to say. That your extension is a radical extension. So, in order to say this extension is a radical extension, what do you say? So, we say alpha in K is solvable by radicals if there exists a extension K over F, or I should say maybe L over F, such that this is a radical extension. Do you agree? Are you trying to say this or something else?
Solvable by radical extension. Okay. Simple radical extension, then we will go to radical.
So each of these are simple radical. Yes. So each fi by fi minus 1, if you say simple radical, then your whole extension L over F becomes a radical extension, right? So for definition of radical, that means you should have a tower of simple radical extension, right? This is how you make an extension to be radical extension. And for solvability by radical mean, you can find a extension where your alpha lies and that extension is a radical extension, right? So some L, we don't know how, sorry.
The condition alpha power ni belongs to fi minus 1 for each
Uh,
f.
alpha power n belongs
Alpha
to.
power ni
Yeah, exactly. That is same. No, that is it's okay. I mean, if
belongs
you're
to belongs to fi minus 1
hmm,
for
is this
every
you're
element.
trying to say?
So this condition is also required for solvable by radicals.
I don't think that is required because you just need in order to say that an extension, okay, a element is solvable by radicals. If you can find the extension, which is radical extension, let's say L over F, if you can find this radical extension where your alpha lies in L, then you are done. If you are able to find a radical extension, and I think what you are trying to say is just uh, making this simple radical extension, because you are saying fi is fi minus 1 alpha I. I think this is what you are trying to say, where alpha I power ni belongs to fi minus 1. This
Yes,
will makes you fi over fi minus 1 as simple radical extension. You agree?
yes,
So I think you're saying same thing, that if you can find a tower of fields such that each consecutive fields are simple radical extensions, if each are simple radical, then this is what exactly the meaning of simple radical, what you said. And equivalently, you get a extension L over F, which becomes in fact radical. Why? Because you have obtained through simple radical extension. And it is equivalent to saying that if you say an element is solvable over F, that means you get a radical extension where your element lies, alpha lies in L. And that is same what you said. So yeah. So either of the things, if you understand, then this is the fact. Yes. All right. So then we know what is simple radical, and now we know how to say that an element is solvable by radical. Now, when can we say an extension is solvable? This is something else.
every element of K is solvable by
Yeah,
radicals.
so solvable means solvable by radicals. Exactly. So let me write now. See, so we say an extension. So let K over F is solvable extension if um, every element, every element K in K is solvable by radicals over F. Now, you know our basic definition of solvable by radical, that means you can write every element as a combination of plus minus multiplication division and taking radicals. And how the things have been changed in terms of field extension, this is quite like celebrating. Anyway, so we will use these results now to check whether a extension is solvable or not. So finally, question. So saying that a polynomial, so let's say, so if somebody asks you a polynomial fx in fx is solvable over f. So what is the meaning of polynomial now? Earlier we have some element in extension. Now we want whether a polynomial is solvable over f or not. Then what is the criteria to check this?
All its roots are solvable over here.
Yeah, so if all its roots are solvable over f. Of course, we don't know where the root lies. So we say that where if all its roots in some, let's say splitting field, splitting field. All right. So okay. Now let's go to question 4. I think we just discussed this part. Let me just rewrite this. So a polynomial fx in kx is solvable if all its roots in some splitting field are solvable over the base field F. Yeah, so can we see some example of radical extension now? Radical but not simple radical. This is important. Simple radical we have seen. Let's see some example of radical extension and radical but not simple radical. Yeah. Yeah. Can you build some example of radical extension?
Like we have seen already that q root 2 over q.
Yeah, that is simple radical also. But let's look at some example which is not simple radical but radical. Simple radical. Yeah. Radical but not simple. So if you recall the definition of radical extension, I think you will get the example. So recall, so we say K contained in, is it K or F? F, okay. So F equal to F naught contained in Fr equal to K. So if K over F is radical, if Fi by Fi minus 1 all are simple radical extension. Yeah. So knowing this fact, I think should give you some example of radical extension, which is not simple. Can you make tower like K containing Q root 2, containing somewhere, and so on, and you reach up to an extension K, and then you say K over Q is radical. Can you build such a tower? Yeah, it's easy, right? If you see like this way, Q root 2, root 3, root 2, root 3, root 5, so on. Let's say I stop at this level, Q root 2, root 3, root 5, root 7, root 11. If I stop here, then of course this is a radical extension. Why? Because you see all are just simple radical extension. This is simple radical. This is simple radical. All are simple radical. And therefore, I can say K, which is Q root 2, root 3, root 5, root 7, root 11 over Q is radical extension. Or maybe, let me see some more example. Q containing Q root 2, containing Q root 2i. This is also a or maybe you can again check I root 3. Keep doing like this. This all are. This is a radical extension. You agree, right? Hello? Hello?
Yes, I'm just noting down.
Okay. So these all are examples of radical but not simple. Now question is why not simple? This is important that these are radical by definition, but why not simple extension? Simple plus radical. Simple plus radical. This is important. So let's write that. So notice that very simple example, let's say just adjoining two elements, root 2 and root 3 over Q. This we know it's clearly a radical extension because it has been constructed through a tower of simple radical extension, but it is not a simple radical extension. So why, I think it's done in the notes also, I'm just repeating very crucial idea. Why? Because it's not a simple radical extension. We know what is the degree. Yeah, what is the degree of this extension?
4.
It's 4, right? Suppose it is radical. So knowing, suppose let's say this is k. Suppose k over q is radical, then there exists some alpha in q, so k, such that alpha power n should be in q, and our k should be generated by q alpha. This is the definition. Moreover, we also know that this n cannot be less than 4. This has to be more than equal to 4. Why? Because we know alpha satisfies alpha. Okay, so we are looking at extension of q. Of course, alpha cannot be in q, otherwise our extension q alpha is q, but this is not the case. Why? Because root 2, root 3 both does not lie in q. All right, so because our q alpha is same as k, and k is nothing but q root 2, root 3. All right, so this cannot happen. Therefore, n cannot be 1. This is for sure. This cannot be. I'm saying n cannot be 2 and n cannot be 3. Both the possibilities are also not there. Why? Because suppose alpha cube is in q, then I should be able to write alpha cube as some m, where m is in q, and therefore alpha cube minus m is 0. Therefore, alpha satisfies x cube minus m equal to 0, right? So, but we know that alpha satisfies an irreducible polynomial of degree 4 because of the degree of the extension. So if we are taking any alpha in k which is outside q, and we are writing k to be q alpha, then the degree of q alpha, sorry, degree of alpha should give me the degree of extension, but degree of extension is 4. Therefore, alpha cannot satisfy a polynomial of degree less than 3 because alpha satisfies irreducible polynomial of degree 4 over q, and therefore any polynomial over q where where alpha is a root, has to be of degree greater than equal to 4. This is because of the degree of extension we know. So therefore, our alpha should be this, or this should be the case. Either this or this should be the case. So now suppose, and in fact, if we say that alpha, suppose we know alpha power n belongs to q, then we also know that, let's say alpha power n equal to a, then I know that the roots of x power n minus a equal to 0 are nothing but, what is, one is alpha and other are alpha zeta, where zeta is, let's say zeta I, where zeta is the primitive nth root of unity. Okay, now why this is the case? Because suppose we know alpha power, okay, suppose we know alpha power 4 is some m where m is in q, suppose. Then that we know that alpha power 4 minus m is 0. That means alpha is a root of polynomial x power 4 minus m equal to, sorry, root of this polynomial, right? Now, if I ask you what are the all possible root, then alpha zeta square, alpha zeta cube, where zeta is the primitive fourth root of unity. You agree, right? Hello?
Yes.
So therefore, if this is the situation, then we should, and we also know that any Galois element, suppose, so I'll just write one more thing. If you want to see this page, I can stay for some time if you want to see something. So maybe I'll just maybe I just repeat everything. So we want to prove that this extension that we have made, this q root 2, q root 2, root 3 of so on, this is not a simple radical extension. Suppose it is simple radical extension, then there should be some alpha such that I can write my k to be q alpha over q. Now, knowing the degree of extension to be 4, we want to know what power of alpha can be in q, because radical mean that some power of alpha should be in q. And we can say very easily that it cannot be less than 4. So whatever n belongs to q, that has to be greater than or equals to 4. But that would give that the all roots of our polynomial, that has to be product of alpha with the primitive roots of unity, nth roots of unity. Now, knowing this all knowledge will help us to build a contradiction. Contradiction to what fact? That this is a radical, simple radical extension. Suppose it is simple radical extension, that means suppose we have this thing. And we have deduced that alpha power 4 belongs to q, or alpha power n belongs to q for n greater than 4. And we also deduce that the roots of x power n minus, let's say m, where m is in q such that alpha power n equal to m, is least n such that alpha power n is in q. Okay, this knowledge we have. That means the roots of our polynomial are nothing but x equal to, roots are alpha, alpha xi, alpha zeta square, alpha zeta cube. These are the all possible roots. If such a situation is there, we know that Galois group of q over q has to be 4, because this is q alpha over q, which is degree of our extension, which is 4. Why? Because we know that q root 2 root 3 is a Galois extension over q. This is Galois. Knowing this all knowledge will give us that I know sigma, if any automorphism is there, then it should always permute the roots. One root is alpha, so one automorphism is this. Another root can be alpha zeta, or can be alpha zeta square, can be alpha zeta cube. These are all possibilities. But you know that zeta is primitive fourth root of unity, or primitive nth root of unity for n greater than equal to 4. This is what we know because of x power n, because of n greater than 4 or n equal to 4. In either case, xi has to be a complex number. Xi had to be xi square, not xi maybe, but xi square. So if you see the primitive fourth roots, then it is plus minus 1 plus minus I. If you see primitive nth more than n greater than 4, again it will have 1 and some other xi such that it's a complex number. So in any case, you will see more than 2 roots has to be a complex number. But your field is q root 2 root 3. That is not, which is a real field, which is not a complex field. Therefore, you cannot map those roots to other roots. That means you don't have all automorphism. That means you just have two automorphism mapping alpha to alpha, alpha to minus alpha. But how is that possible? Because our Galois group is order 4. So therefore, you cannot have an alpha such that your extension is a simple radical extension. It has to be a radical, of course, but cannot be a simple radical extension. So the whole crux of the story is we took a degree 4 extension. The whole story came into picture because of degree 4. If we land up to degree 2, we saw it is simple plus radical. Because here we know the roots are plus minus root 2. Both are real roots. As long as you cross your degree more than 2, degree 4, then your roots, if it is a simple radical, then your roots should be complex roots. And in that case, you won't have all Galois elements. I mean, you don't have all automorphism in your Galois group. So, it cannot be a simple radical extension. Anything, and in fact, any degree now, you see q root 2, root 3, root 3, root 5, root 7, root 11, all degrees are more than 4. All will have the same issue, and therefore they cannot be simple radical. This is okay, right?
Thank you.
Okay, so I think this is little bit messy, but therefore once you have degree more than 2, it's always a challenge to check whether extension is simple or simple radical or not. Okay, so I think the question is done, I think more or less. Yeah. Question 5 is, suppose K over Q is a simple radical extension where K is the splitting field. Okay, we have to check whether K over Q is a simple radical where K is the splitting field of some polynomial x cube minus 3x plus 1 equals 0. So I have written some polynomial and there is some speciality about this polynomial that one has to see carefully.
All three roots are real.
Yeah, it's very nice thing about this polynomial that, okay, let's discuss first. I think I have written here, huh? Or let me try to explain. If we have fx to be x cube minus 3x plus 1, how do we see it has three real roots? Yeah. So in order to say real root, that means there is some r1, r2, r3 in real line such that f of r1, f of r2, f of r3 is 0. This is the meaning, right?
Yes.
If that is the case, we draw the real line now. If you are saying that there is r1, r2, r3, then there should be 3 points on the real line where the image is nothing but 0. This is 0, this is 0, this is 0. Do you agree?
Yes.
So there should be, this is what I want. How can I say that the there will be 3 points which will cut the real line? Yeah. If we can say there are 3 distinct points, in fact just 3 points which will cut the line, we are done because the degree of the polynomial is 3. It cannot have more than 3 roots because we are in field, not in ring.
You can sketch the graph of.
So we want to draw the graph. So how would we draw? You know, drawing a graph for a degree 3, degree 2 maybe, or maybe easy. That's not very difficult. Drawing is not difficult. But how to choose the correct points so that I will get the 3 real roots? Yeah? So hint is, if you can say that there is a point, if you can say, if you can use mean value theorem, it says that if you have, okay, let me write this way. So if you can find x and y, maybe not x1, something else, some y1, y2. So let there exists some y1, y2 in R such that f of y1 is less than 0, less than f of y2. Mean value theorem says there exists a C in R such that f of C is 0. And this should be because of you are working over f continuous on some, let's say, closed bounded interval, and this is what the thing you have. Anyway, you know that f is polynomial, so it is continuous everywhere, it is continuous on any domain. So yeah, so you can use this theorem. That means you want to construct, you want to build 2 points such that function values are negative for 1 point, function values are positive for 1 point. This means that your function values is negative. This means that your function values are positive. So can you find that? This is what the final goal is. Try to find the points on real line such that you can say the image of your function is nothing but negative for 1 point, positive for 1 point, and therefore your graph. This will give me that there is a graph which is going negative first, which is going negative. So negative, these are negative values, these are positive values, this is 0. So your function is going negative first, and then you are saying there is a point which will make it positive. That means there is a cut. There is a cut. Again, you are saying there is a point which will at which the function values is negative, that means you have to come down. That means it will cut it. Again, if you can find me some point which is negative and positive, then that means you have to go positive. Again, it will cut at some point. So this is all about now finding the correct points. So I'm giving you some idea. Let's say if you try to look at f of minus 2, f of minus 1, f of 0, f of 1, f of 2. You can quickly tell me what is this, right? Because your fx is x cube minus 3x plus 1. Yeah, what is f of minus 2?
Minus 2 is it is negative.
It is negative. It is minus 1. What about f of minus 1?
F of minus 1 is positive.
It's positive. It is 3. Yes. So you got something, right? Okay. Now about f of 0.
That is also positive.
That is also positive. That means there is no root between this and this. That you can see, right?
Yes.
0 minus 0 plus 1, which is 1, which is again positive. So you cannot, there is no sign change. What about
F
f
of
of
1
1?
negative.
Minus 3 plus 1 is minus 1, which is again negative. There is a root here. There is a root here. What about f of 2? Yeah,
F of 2 positive.
it's positive, right? So it is 9 plus 6, 3 positive. All right, so this will give, there is a root here also. Once you get, and you also know that the points are distinct, right? Your intervals are distinct. So between minus 1 and minus 2, you saw minus 2 and minus 1, there is a root. This is what mean value theorem says. You got your y1 this, you got your y2 this, such that function values is negative for y1, positive for y2. Therefore, there exists some point lying here, some c1, or let's say r1. We need r1. Again, this is, there is no change between minus 1 and 0, but there is a root between 0 and 1. So there is 0 to 1, there exists some r2. And similarly for f1, f2, there is a sign change. You will get a root between 1 and 2. And you can see the roots are distinct. And you have degree 3 polynomial. So you got all three roots and all are distinct also. This is okay?
Yes.
Alright, so this is how we will get that our splitting field is over Q should contain all three distinct realities. It's also distinct. Alright, this knowledge we have. Can we use this knowledge to say something that whether the splitting field gives me a simple radical extension or not? Can you say something about that? So notice this real is very important. Recall previous result Q root 2 root 3. It's a degree 4 extension, but it is a real extension. Now again we have something similar. Your splitting field. So let's say K is the splitting field. So K splitting field of F. That is also real now. Why? Because all your roots are real. Can you use this fact to say reasoning is almost similar that we gave in the last question also? Can you say this is a simple radical extension? Yeah. So first of all, what possibly can be the your degree of the extension? Yes. Can we say something? Suppose I ask you x cube minus 2. If we see, then here the splitting field has, let's say k is the splitting field of this, and k over q, you know that degree is 6, right? But if I ask you x minus root 2, x minus root 3, x minus root 5, if I ask you the splitting field for this polynomial, clearly you can say that k over q has degree 3, right? sorry, what I'm saying. Yeah, what is the degree? Again 6. But let me see, what is the example? Hmm. Okay, then I think we have to go to the polynomial. Okay. So can you say something about this polynomial? Is it irreducible? Because this will tell me the degree of the extension.
You can use the Einstein criterion.
Yeah, so here we can use the Eisenstein criteria. So notice that K over Q is a degree 3 extension cos x cube minus 3x plus 1 is irreducible by Eisenstein criterion. Alright, so this we know. Now knowing this degree, earlier also we know the degree and degree helped us. Knowing this and knowing this, can we say something? Is it simple radical? Repeat the same argument that we gave. Yeah. So suppose it is simple radical. That means there should be some alpha. So there exists some alpha such that alpha power cube is in Q. Or let's say alpha power n is in Q for n greater than equals to 3. Although we know that this is true because of the degree. Now if that is the case, then our sigma, which is from Q alpha to Q alpha, should map roots to roots. Now roots are nothing but either alpha or some alpha times xi. Now if your n is 4, let's say, then you know that xi is plus minus 1 plus minus xi. That means you can map alpha to minus alpha also because you are in n equal to 4. But if you are suppose n equal to 3 and even in fact n equal to 4, you cannot go to alpha dot xi square where let's say xi is I. You cannot map to, I should say here zeta square. This is zeta. Alpha dot zeta cube where zeta is I. You cannot map to this because your field K is a real field. Same thing if you have, let's say, n equal to 3 and suppose you want to map Q alpha to Q alpha, then alpha either can go to alpha or it has to go to alpha zeta where zeta cube is 1. Again, it's not possible. Why? Because your K is in real. So in all this situation, it's all about knowing that whether your extension is a real extension or not and what is the degree of your extension. As long as your field is your splitting field is a real field and degree is 2, you are safe. If your splitting field has degree more than 2 and is not real, there is no possibility you can make it as a simple radical extension. So therefore, just a remark, uh, a degree 2 extension is always a simple radical extension. A degree, let's say more than 2 extension, say K over F, is not simple radical if K is a real field. So once you know these two things, I think it's simple to check whether the extension is simple radical or not. So I think it's clear, right?
Yes. Yes.
Okay. Now if I ask you, is the extension Q 2 power 1 by 3 omega over Q a solvable extension? So recall what is solvable. Yeah. So let's go back to the definition of solvability. So we saw extension is solvable if every element is solvable by radicals. And solvable by radical, that means your element should lie in a radical extension. This is what we want. All right. So let's go to Q2 per 1 by 3 omega over Q. Is it a solvable extension?
Just a minute, I will copy that remark.
Sure.
Remark. A degree 2 extension is always a simple radical. A degree 2 greater
Well,
than
I
2
should say
extension.
characteristic not equal to 2.
K over F is.
So we are all inside characteristic 0 field.
Yes. Oh, characteristic not equal to 2, the condition.
Yeah.
So Q is of characteristic 0, right? Degree 2.
This is okay, right?
Okay, now
Okay.
you can proceed.
Yeah, sure. So, what was the question that we were dealing? Yeah. So B part of this question says, is the extension Q2 per 1 by 3 omega is a solvable extension? So remember, solvability means every element of your extension should be solvable by radical, and your every element that should lie in a radical extension. That should lie in a radical extension. So is that so?
So this is degree greater than 2 extension.
It's a degree greater than 2 extension, yes. But we are looking for solvability, not for simple radical. So remember that earlier we were checking simple radicality of an extension. Now solvability of an extension. Solvability means you have to check every element to be solvable over the base field. I'm saying there are two ways to check this. So if you see, there are several results on the extensions, and if you suppose want to let's say solve some question based on some result, then it's good to write all the result on a single paper. So if you see, there are many results, let's say about cyclotomic, Kumar extension, cyclic Galois extension, solvable extension, and then radical, simple radical. So if you can write the results on a single paper, or let's say some 2-3 papers, then it's good that you always recall those, and then you can quickly use those results. So one thing that this is degree 6. This is one hint that I'm giving you.
Degree 6. So there is a result regarding degree 6 extension.
Yeah, what is that?
Degree 6 extension.
Well, let me recall the result now. So result says, let K over recall K over F be a Galois extension such that the degree of K over F is 6. Then K over F is solvable. It's always solvable. Now, so going back to the question is this. So now can you say about solvability?
So this is K over F is of degree 6.
It's a degree 6, yes. Why? Because it is
degree 6.
This is degree 3, degree 2, degree 6. Yes. One has to check, is it Galois?
So the number of automorphisms on K leaving every element of fixed is also 6, I think.
Yeah, it is 6. Yes. There are maybe, the way you are checking is little difficult. So going to check that whether Galois group is exactly 6 elements is little difficult. But if you can see, it is a splitting field of a separable polynomial. It's done, right?
Galois, that is.
So x cube minus 2 is the polynomial. If you see, it has root 2 power 1 by 3, 2 power 1 by 3 omega, and therefore it is a splitting field for this polynomial. And this is separable also. So therefore, it is Galois. Yes. Galois. And therefore, directly you can say that this extension is separable. Now, if I ask you, don't use this theorem. Use your definition of separability. Uh, sorry, solvability. Definition of solvability says you take any element in your K 2 power 1 by 3 omega. Is it separable? Sorry, solvable. Confused with separability. Is it solvable? So is alpha solvable by radicals over Q. So as you know, the generators are this. It's quite easy to check the generators first. So if I ask you this, is it solvable by radical?
Yes.
Clearly, right? It is solvable by radical.
2 is in Q and it is radical.
Yeah.
2 power
Yeah.
1 by
So
3.
correct. Solvability by radicals means that, of course, you can say that there are several ways, but then one way is that you can check that whether there is a extension of your, let's say, tower of fields. If you use the definition of tower, then this is one should get that here should be your alpha. So can you get a tower of extensions where that is a simple radical extensions tower?
So Q of 2 power 1 by 3. Q contained in Q of 2 power 1 by 3 contained in Q of 2 power 1 by 3 omega.
Okay. So what
This
if
is 2 power 1 by 3 comma omega or 2 power 1 by 3 into omega.
okay? So this is how you are trying to say that this is this simple? Yeah, is it simple? It's degree 3. Remember, it's degree.
Because this 2 power 1 by 3 power 3 belongs to Q.
2 power 1 by 3 power 3 belongs to Q. Exactly right. So it's a radical and it is generated by a single element. Yes, this is simple radical. What about this? Why? Because omega cube is 1.
The same thing.
Right. So therefore, yes. So there are several ways to check that it is actually solvable. So therefore, answer is yes, it is solvable extension. All right. Now we go to question 6. It says, what are all equivalent statements to prove alpha in F contained in C is solvable over F? So we know one definition that in order to check the solvability, you need to check that there should be a tower of simple radical extension and your alpha should lie in a radical extension finally. Can you give me some more equivalent conditions to check?
in terms of algebraic over F.
Yes, we are given that alpha is an algebraic over F. Yes. Otherwise, we cannot even talk about that. So one definition says that we have tower of simple radical extension.
Or
This
we can, is it possible to express alpha using the elementary operations and radicals of elements of F?
Exactly, that is one more way, yes. So I will write, okay. But I'm saying there are some more equivalent ways to check which given by Galois. So this definition of that finding a tower where it is lying as a solvable inside a radical extension, that is just the definition itself. Let me write, okay. So we say alpha is in F is solvable by radicals is equivalent is same as um, expressing alpha as combination of and maybe I should write expressing alpha as in terms of plus minus multiply divide and radical and radicals of elements of F. So I think you mean what I want to say here. And the other equivalent definition says that there exists a tower, or maybe there should exist an extension L over F. Alpha is in L, and L over F is a radical extension. And by definition of radical extension, that means we should have a tower. So F naught equal to F contained in F1 contained in R, which is L. Here it is alpha. So, and this should be simple radical. Simple radical. This is all. This all mean that L over F is a radical extension.
Yes.
I'm saying there is another. Yeah.
Okay. Alpha in F.
Alpha in
an
F.
extension.
Well, but I'm taking the extension. Sorry. I should write K over F, huh?
Alpha belongs to K. K is an extension of F.
Yes.
Is separable, solvable by radicals over F.
Yes, over F. Thank you. So, is K is solvable as such? Yeah, I think it's correct. All right. So I'm saying there is one more way to check this whether there is a this element is solvable by radicals over F or not. In recent notes, if you see, there exists an extension L over F, now cyclic, not just radical. If you can find a cyclic extension such that I should say no. Can you recall some result like this? So notice that if you have this, then that means you are all L over Fi over Fi minus 1. These are cyclic extensions. I think this is clear, right? Actually, we mean cyclic extension. That means we are saying that this is Galois. And
Galois plus that Galois group is cyclic.
Exactly. And if you are not able to find a cyclic extension, still you are safe if you can find a abelian extension. So it is equivalently, I'm saying, so there exists a tower, let's say F equal to F naught containing Fr equal to L, where alpha lies such that all Fi by Fi minus 1 are abelian. If you are not able to find cyclic, then if you are able to find abelian, that is also okay. So let's try to see our element. Okay, let's try to see the example now so that we can see. So q2 power 1 by 3 comma omega over q. We know this is a solvable extension by degree also 6, and it is a Galois extension either by using result or directly. And we know that there is a tower of extension. So first of all, if you can say that it is, of course, this is not Galois, right? Not Galois. But this is Galois. And q2 power 1 by 3 over q. Can you say is it cyclic? Yeah. You cannot say, right? So therefore, sometimes you don't know how to use this. You may
Now
not be
this
able to. Yeah.
that g of q of 2 power 1 by 3 comma q consisting only identity, right?
Exactly. So Galois group of, not I should say Galois group, the group of automorphisms of q root 2 power 1 by 3, which fixes q, is just trivial. Yes. Because our extension is a real extension and the degree is 3. So therefore you cannot use this second criteria to check whether this is solvable or not. So sometimes very carefully one has to use which criteria will help us to prove the extension is solvable or not. Anyway, so let's go to part B. Justify why a polynomial is solvable if it is degree 1 or 2 or 3. So for degree 1, degree 2, degree 3, it's very easy to check whether polynomial is solvable. And if you recall, in order to say a polynomial is solvable, you just have to see whether its roots are solvable or not. So let's check. So degree 1. So that polynomial has to be like this form, right? And where does this polynomial lies? In fx. And you are talking about k over f, let's say. Is it separable? Sorry, solvable? What are the roots, first of all?
Only a which is in f.
Yeah, only a which is in f. So does there any question of solvability?
So it's automatically solvable.
It's automatically solvable. Exactly. So this part is trivially solvable. Let's look at the degree 2. Degree 2. A general degree 2 polynomial I can write like this. Whether, I mean, one wants to write, one can write like this. But then the roots of this polynomial will not change if I divide this whole thing by 1 because
Quadratic formula.
Yeah. So you can simply change like this. So I'm just writing now, I'm just rewriting all this to degree 2 like this. Suppose we have degree 2 like this. Now we want to check whether it is solvable or not. That means roots are solvable over f. Suppose my f is, let's say, q. Actually, we want f to be contained in C. In particular, we are taking q. Is it solvable? First of all, what are the roots?
Minus a plus or minus.
Sir, minus a plus minus.
Minus a plus or minus root of a squared minus 4b b squared. A squared minus 4b whole divided by 2.
Correct. Now, suppose we take these are the roots alpha 1, alpha 2, one is plus, one is minus. Then, how do we say that its roots are solvable?
Because A, B are all rational numbers.
Yeah, they are
So
rational.
square root of rational minus A is another rational, plus sign minus sign division 2 is
Exactly.
rational.
Exactly. So we are just having the definition of solvability, that if you can write your roots as some combination of plus minus multiply divide by elements of
Yes.
q or radicals of q, then it is solvable. Exactly. So clearly you can write your q. Let's suppose somebody asks you k over q is the splitting field of this polynomial f over q, then you will write simply k to be q joined by b square minus, sorry, a square minus 4b. That's it. This will give you the extension. But it may or may not be degree 2, depending on your polynomial is irreducible or not. So if it is having root, that means your polynomial is not irreducible. In that case, your degree is 1. And if it is perfect square, that means you have roots over q. Sorry, I think I'm confusing. If a square minus 4b is in equal to m square, m is in q, then k over q is degree 1. K equal to q. If a square minus 4b is not equal to m square for all m, then means k over q is degree 2 extension. Yeah, so in any case, we know it is solvable. Question is, if I go to degree 3 polynomial, then what will happen? Suppose degree of f is 3. Then can we use some result or something, or to say something?
So we can use that Cardon's formula.
Okay. So you are going to use this formula in order to say, okay, suppose somebody doesn't know. This is what I'm trying to say now. Suppose we don't know what is the formula, because I don't remember. If you ask me now, I don't remember the formula. But I know that the roots are nothing but in terms of radicals. So there should be some more way to say that this polynomial is solvable. For any f, where fx of course lies in fx, where f is in C, the sub-sum field of C, then we are saying f is solvable over f. This is what my claim is. If you remember, if you try to remember that if I ask you a splitting field of, suppose k is splitting field of degree 3 polynomial, and if I ask you the extension degree, can you tell me what possibly can be this extension? Yeah. Can
Less
you
than
tell
or
me
equal
some
to
of, yeah, less than equal to
3 factorial.
3 factorial? Yes. What is that?
6.
6. So possibility of your extension is either it is degree 1, 2, 3, 6. You agree? In fact, k over f divides this. Not just this, it will divide this 6. Now, knowing this fact, suppose degree is 1. Are we done?
K equal to F in this case.
We are done, right? Why? Because
Yes. Every element of K is.
exactly. Then you should be able to write your fx to be x minus a1, x minus a2, x minus a3, and all ai's belongs to k. This is that case. This is this case. And these are clearly roots are nothing but elements of K, so this is solvable, very clear. What about degree 2? I'm saying this is also done. Suppose degree is 2, then polynomial is like this, right?
So that we have seen already.
That we have seen. For this also, for this also. We know the roots here, both are there. If I say degree 3, there are two possibilities. It can happen that your degree 3 polynomial factors in degree 1 and degree 2. This degree 1, this is degree 2. Or it can happen it is irreducible over your field, let's say f. Suppose this is the case. Are we done in this case?
That is the K over F is 2 means how can you write as product of two quadratic expressions? How can
Sorry,
you
I'm
write
not.
product of two quadratic?
Sorry, it should be product just 1 degree. Yeah. Sorry. And you should be able to write your polynomial like this time. No, but our degree of f is 1, so I should be write like this x minus. Where c is an f. Yeah, I should write like this. This is okay, right?
Yes.
Now, if I have degree 3, then either it is degree 1 polynomial and degree 2 irreducible polynomial, or it may happen that degree 3 itself is this polynomial is irreducible. I'm saying for this case, you don't have to check anything because this is same, right?
Yes.
Question is if it is irreducible. I'm saying this is also simple. So notice that if you have k over f is 3 and fx is irreducible, that means your k is a cyclic extension. Do you agree? Because in this case, your Galois group k over f is nothing but order 3 and it is cyclic group z mod 3z.
The
Do you
group
agree?
of prime order is cyclic.
Exactly. But we saw an equivalent statement that if you want to check an alpha to be solvable, it is enough that you can find a cyclic extension where your alpha lies. Yeah, if you can find an extension which is cyclic and L over K, alpha belongs to L. Same thing here. Now we have a cyclic extension K over F and alpha lies in K. Is this okay?
Yes.
Okay, so I think this case is also perfect fine. Now remaining is K over F is degree 6. But we know that degree 6 Galois extension is always
Yes.
solvable.
That result is.
So therefore degree 3, if you have degree 3 polynomial and you want to check it is solvable over a characteristic zero field, it is always solvable. So let me write. So polynomial of degree 1, 2, 3 over characteristic zero field is always solvable. In fact, we will see something about degree 4 also. Alright, so this is one question. Other question is, suppose we have a H, a subgroup of Sm. When do we say H is a transitive subgroup of Sm?
Madam, the screen is not moving.
Screen is not moving, really? Okay. What about now?
Yes.
Can you see the question?
No.
Okay, let's wait. Is it visible now? Can you see my pointer?
No.
Okay. If once you see the question 6 part C, tell me.
No, madam.
And I will go back and I
It
will
got
stop.
stuck in the previous slide.
Okay, I will stop sharing and then I will start sharing again. I hope that it should be visible now. Is it?
Yes.
Can you see question
C.
6? Yeah. Okay. So question is, if you have a subgroup H of symmetric group of n symbols, when do we say H is a transitive subgroup of Sn?
Transitive.
Yeah.
So for any two given indices ij, there must be a permutation sigma in Sn such that sigma of I equal to j.
Well, as if you say sigma in Sn, then I will say that is always the case. Given any two indices, you will get a element sigma in Sn such that sigma is same as j. You have to be little more precise.
Transitive.
Yeah, transitive, but about of subgroup, not group.
The class they have given the definition, I think only like that. Transitive subgroup.
Well, I think then you must be confusing with the definition. Maybe I will recall, okay? So, yeah, let me recall here. So, solution, C part. So, we say suppose H is a subgroup of Sn. What do we mean by first of all Sn? Let's recall the group Sn. So, group Sn is nothing but all sigma from, you have set of n symbols to n symbols, and sigma is a bijection, right?
Yes.
This is the definition, and of course the operation is composition. And we are talking about H to be a subgroup of Sn, so we say H. So we say H is a transitive subgroup of Sn if given any two elements, let's say I and J, anything from the set 1 to n, such that there exists sigma in H, not in Sn. This is important. Is in H,
Yes.
not in Sn.
Such
that sigma I is J. Exactly. I mean, of course, you should be able to find sigma. You will always find in Sn, right? Sn, you will always get it.
Yes.
The point is about getting in H.
H.
Yeah. So this is the definition of transitivity. So then we say it's a transitive subgroup. Now, knowing the definition, let's go to question number 7. It says, what is the Galois group of F over F, small f over capital F, where degree of F is n? Yeah. So suppose we know that degree of F is n. Can we say something about the Galois group of F? So, what is the definition first of all? The Galois group of a polynomial over F. This is definition.
That is Galois group of the splitting field of the polynomial.
And why we are talking about Galois group? Because Galois is only stand for extension to be Galois extension, right? But if you just take the splitting field of the polynomial, how can it be Galois? So you just said Galois group of F is Galois group of splitting field of polynomial over F. But Galois group does not make sense for just splitting field. It makes sense when your extension is a Galois extension. Of course, your definition is correct, but I need argument why splitting field is enough. So if you recall, we are working over field in C, right? We are working in characteristic zero field. Do we need to check separability?
No, because every polynomial over Q is
Separable. Exactly. So you just need a splitting field only to construct a Galois extension, and then you can talk about its Galois group. So exactly right. If you said so, solution A. So we say the Galois group of polynomial f over f is the Galois group of splitting field, say k of f over f, that is yeah. So I think it is clear. Now we know this. Question B, can we find a group G where Galois group of a polynomial is contained as a subgroup of Sn? Oh, sorry. I think what I'm saying, can we find a group G where Galois group of the polynomial f is contained as a subgroup? Yeah. So, okay, let me just tell what I want to say. Galois group of f is contained in G. Can we find this G where we know that it is always sit there? Always sit there.
that if K is the splitting field of F, then capital G is Galois KF.
Galois KF, okay. So, okay, this is the splitting field. That means this is nothing but Galois K over F, where K is the splitting field. This you know. I'm saying, can you find this group G? I'm saying this is always fixed. Fixing one polynomial of some degree n, let's say, you can always tell me where does your Galois group of polynomial sit as a subgroup of that group. So I'm saying this group is always fixed once you fix the degree of your polynomial. So let me repeat. Given a polynomial of degree n, we can talk about its Galois group. That is same as the Galois group of its splitting field. I'm saying you can always get a group where this Galois group sit there as a subgroup. Okay, let me just recall something. I think you will recall now. You will remember. So if you see, if you remember, if I have K is a splitting field of degree n polynomial, splitting field of degree n polynomial, what is possibly the degree of K over F? Can you give me the upper bound for that?
N factorial.
Can you give me a group has order this n factorial? Can you tell me a group having order n factorial?
That Sn.
Exactly, Sn. So the statement is, if F has degree n, no matter it is irreducible or reducible, your Galois group of F is always sit as a subgroup of Sn, always. And the hint is you can use this one to tell this. This one way to remember the statement. Now, if F is irreducible, next question is, okay, let's leave that. Look at part C. What is the Galois group of this polynomial given x cube minus 3x plus 1? Yeah. So do you know anything about this polynomial? Any result about this polynomial?
All roots are real, we have seen.
All roots are real, distinct and real, yes. Anything else you know? Reducibility, irreducibility.
This is separable.
So separable, of course, yes. Because it is over characteristic zero field, it will be separable, yes. Saying it is irreducible. You remember we did this fact that it is irreducible by Eisenstein criteria.
Yes.
So this, in particular, this polynomial is irreducible, and if you remember some result that given polynomial is irreducible, then not just that it is subgroup of Sn, it will have some more condition. Can you recall that there is one proposition? If you have F irreducible, then you can tell me whether your group, Galois group of your polynomial, not just it as a subgroup of S3. It will be a subgroup of S3, we know that. You can tell more about that group. So let me recall. So if this is whenever any degree n polynomial, this will satisfy. But in particular, if f is irreducible of, let's say, degree n, then it will be isomorphic to a transitive subgroup of Sn. H is transitive. Do you agree? This is one result I think Sir has given in his notes. Given f irreducible, degree n, that is always isomorphic to some subgroup which is transitive subgroup. Now, knowing that our polynomial x cube minus 3x plus 1, this is irreducible, and what is the degree of the polynomial? It is 3, right?
3.
So G, our Galois group of polynomial, has to be isomorphic to some transitive subgroup of S3. So the question next is, what are all possible transitive subgroups of S3? Now, what is the order of S3 first of all?
6.
3 factorial 6. And Lagrange theorem says if order of H divides order of G, if H is a subgroup. So what is the possibilities of order?
1, 2, 3, 6.
This is S3, we know. This is trivial, we know. Can you say something about these two groups? Yeah. So recall S3 is this group. So order 2 subgroup and order 3 subgroup. Can you make out of this?
Yes. 3 order 2 subgroups.
3 order 2 subgroups, yes.
1 order 3 subgroup.
1 order 3 subgroup, yes. This is, let's say, H3 or H4 maybe. This is H1, H2, H3. Now, which one do you see that those are transitive subgroup? Of course, this isomorphic to A3 also. So our A3 group has order 3 factorial by 2, which is 6 by 2, 3. So this is same as alternating group of order 3. Now, which one is transitive? Recall the definition. Given any indices I and j in 1, 2, 3, there should be a sigma in H, whichever H you are saying transitive, such that sigma I is same as j. It's very easy to see from the collection of subgroups that we have. Can you see what are the transitive subgroups here? If I ask you H1, if I give you two elements, 1 and 3, can you find me a sigma in H1 such that 1 maps to 3?
In H1.
Yeah, H1 means this is sigma which is from 1 to 3 to 1 to 3, where 1 goes to 2, 2 goes to 1, 3 fixes. This is the definition of 1, 2, right? 1 goes to 2, 2 goes to 1.
Yes.
3 is no change. But if I give you two pair, let's say 2 and 3, Can you find a sigma which maps 2 to 3 or 3 to 2
No,
in H1? In
no.
H2?
In H2 you can find out, but for some other pair it is not true. For 1
Oh.
and 2,
Hmm. No, even in H2 is also not true. If I ask you 2 and 3, with the same pair, 2 and 3,
yes, not possible.
it's not possible. But
So,
if I ask you for 1, 3 in H3, it is not possible.
yes,
So clearly H1, H2, H3 are not transitive. But what about H4?
in H4 you can find out.
You can find out. So this is only transitive, non-trivial subgroup of S3. You agree?
Yes,
So now going back, this is degree 3 polynomial, and we know by result the Galois group of this is isomorphic to a transitive subgroup of S3. And what is that? Can you say that? Yeah.
at H4,
H4, which is A3, exactly.
A3.
Yes. So this is A3. So therefore you can say, now finally conclusion is Galois group of your F, which is x cube minus 3x plus 1, is isomorphic to A3 as a transitive subgroup of S3. This is okay, right?
Yes,
All right, so let's go to part D. If F is reducible over F, will the statement saying that Galois group of F isomorphic to transitive subgroup of Sn, will that still hold? If I change by reducibility, irreducibility by reducibility. So our statement, if you recall, if you have irreducible polynomial, then only
yes,
Galois group is, yeah. What is your guess? Yes or no?
yes.
Well, answer is no. The results will not hold if you replace your irreducible polynomial by reducible. So let me just give you quickly. Note that this is irreducible over here.
Yes.
And therefore Galois group is isomorphic to a transitive subgroup. But let me give you a polynomial x minus 1 x square plus 1. Is it irreducible?
It is reducible.
It is reducible. First property is this. Now, if I look at the Galois group, okay. Now, how do you see the Galois group first of all? So, we are trying to say the Galois group of F has to be isomorphic to. The definition says the Galois group of this is isomorphic to Galois group of splitting field of F over Q, right? Can you tell me the splitting field of this polynomial?
It is C.
It is
C.
C, but then
Q,
actually,
Q of I. Q of I.
yeah, we need the smallest, minimum splitting field. So
Q
Q
of
of
I.
I over Q, and we need Galois over this. What is the degree of this Galois group?
2.
2. Now, is degree 2 polynomial, sorry, order 2 subgroup, transitive subgroup, does it exist in S3?
No.
So, does the result hold? This is not isomorphic to. So, cardinality of this is 2, and which therefore the Galois group of F is isomorphic to C2, which is not a transitive subgroup. Transitive subgroup of S3. This is okay, right?
Yes.
So answer is no, that if you change
No.
your irreducible polynomial by reducible, result will no longer hold. Will no longer hold. Okay, let's do this last question, then we will stop. I think time is up. Define discriminant of a polynomial. So suppose you have a polynomial f in fx and degree of f is n. How do you define discriminant? Yeah.
Discriminant of a polynomial. That is a product
Yeah, exactly. Product of
alpha I minus alpha j whole squared.
product of alpha I minus alpha j square.
I less than j.
And what are alpha I, alpha j?
Alpha I, alpha j are the roots of that polynomial.
They are the roots lying in splitting field of f. Exactly. So we need all roots wherever they are lying. We don't care about that. We just need all roots. As long as we have roots, we take the product of the square of the roots. This is discriminant. Exactly. Now, if I ask you part B is x power 4, we have fx is x power 4 minus 1 is in qx. What is the discriminant of this polynomial?
First, we'll have to find out the roots.
Yeah, can you tell me the roots?
Roots are 1 minus 1, I minus I.
Yeah, so what are the discriminant now?
So you can name them alpha 1, alpha 2, alpha 3, alpha 4.
Okay, tell me what is alpha 1, alpha 2, alpha 3.
1 minus 1, I minus I.
This is your order, okay. Now let's try to write
So
alpha 1
the
minus
first
alpha 2.
term is 2, 2 squared. 1 minus I the whole squared. 1 plus I the whole squared. Minus 1 minus I the whole squared. Minus 1 plus I the whole squared. 2I the whole squared.
Exactly. And this you can solve, right? So take the product and then you will get the discriminant. All right, so this will give you the discriminant. This is how we find. Now question is, I think I want to ask some more thing, but that will depend on what is the discriminant. And I don't want to spend time for solving this. Anyway, you will realize that your discriminant, if you see here, it is an element of C. If you, it appears to you, it is an element of C, right?
Yes.
But it will land up, if you will see yourself by computing, discriminant will actually be lying in Q. This will no longer be a element of C. In fact, it will be a Q.
So the final answer will be independent of I.
Yes. So important fact is, if you have K over F as an extension, if you take discriminant of any alpha, where alpha is in Q, K, and discriminant of any alpha belongs to, sorry, discriminant of, sorry, F. Always belongs to your base field fx. Sorry, f. It's a scalar, so it always belongs to f. And the important fact is, sigma, if you see product of alpha I minus alpha j, you know that sigma, all sigma in Galois group, if sigma of x is equal to x, for all sigma, that means x is in f, right? Here also you can see sigma of discriminant is always discriminant for every sigma, implies that discriminant is in base field f. This is the fact. And I think you can, same thing you can use to fact what is the discriminant of this. Now I just want to take one more minute. You know, you can find the discriminant of this f, right? How? By definition. Definition says you find the roots first. Can you quickly tell me the roots here?
Roots here minus 1 plus
It's
or
x
minus.
square plus x plus 1. This is your fx. What is discriminant?
The roots are omega and omega squared.
Omega and omega square. Now let me write alpha 1 to be omega, alpha to be omega square. If I ask you what is the discriminant, can you tell me?
That is omega minus omega squared whole squared.
What is that?
This is omega squared minus 2 minus omega plus omega minus.
Plus omega, right?
Yes. That
Okay,
is
can you?
minus 3.
This is a rational number, right? Even if your omega and
Yes.
omega cube is in, sorry, omega square is in C. So notice discriminant is always in the base field.
Yes,
But I'm saying you don't have to do all this. For quadratic equation, usually discriminant of finding the roots is same as discriminant of this polynomial. So what is the discriminant by definition? Finding the roots.
Discriminant is b squared minus 4ac.
B square minus 4ac. And what is that?
Here 1 squared minus 4.
Is it same? Is it matching with this number?
Yes.
So indeed yes. So for quadratic equation, discriminant of f, which is product of alpha I minus alpha j square, is same as b square minus 4ac if your f is x square plus bx plus c.
No, ax squared plus bx plus.
Sorry, ax square. Exactly. So I think I will end it here itself. Okay, then I have some more questions, but I think I will discuss later.
Okay, madam. Thank you very much.
Okay. Thank you.